Today we're going to continue talking about the problem that we considered last time. So we were building up our system for proof of stake, and we saw that one of the main problems there is how to generate randomness. And just remember that we had a situation like this. We had different epochs, and each epoch was not only responsible for adding new blocks, but it was also responsible for creating the randomness for the next epoch. And we talked about the randomness generation or random number generation problem that we have, and we talked about the security requirements that we need. So we said that we need the numbers to be generated uniformly at random, we need them to be independent, we have to reach some consensus about them, they should be unpredictable and tamper-proof. And at the very end of the last session, we also added these two extra assumptions. One was that we will have constant runtime, and the other is that we should have a guarantee that we will always have a result, a random number. So let's talk a little bit more about these two, and then I will talk about another way of generating randomness. Okay, there is a question here regarding the project. Can we use the codes such as blind signatures provided on the internet with citation as a framework to start without completely beginning from scratch? No, you have to write all of your code on your own. So you can just use basic Solidity, but you cannot use any code that comes from anywhere else. Okay, so here, going back to the problem of generating randomness, we saw a naive example of why we cannot use the hashes as our source of randomness and how the miners can tamper with that. And then we saw one solution for generating randomness, which was based on a commitment scheme. Now, the problem we had here was that some players, some malicious players might decide not to reveal their numbers. So player MI might decide not to reveal this number XI, because it might be the case that they see it, if they reveal, the result would be worse for them than if they don't reveal. So we talked about this and said, okay, the solution that we can have is that we can have deposits from all of the players, and these deposits can actually be the stake that they're using to take part in this random number generation. And if someone does not reveal, we will just confiscate their deposit or burn their deposit. But this is not great because it might be the case that, first of all, someone does not care about their deposit that much. So this only works if we assume all the players are rational and they really want to maximize their own payoffs, and that the deposits are large enough to cover any other kind of money that the player can make by cheating. So we need a lot of assumptions for this to work. And the worst case is that, well, the player might be just malicious and they might want to make sure that we cannot generate our randomness at all. Maybe the player's goal or that miner's goal is just to destroy our blockchain, and they don't mind paying a fee for that. So in that case, what would happen here is that basically we will fail in generating randomness in time. And because we fail in generating randomness in time, let's say in epoch 2, we fail to generate the randomness that we need for epoch 3. But as soon as that happens, our blockchain is dead, because then when we go to epoch 3, we don't know who the miners are going to be. And so there's no one who can mine new blocks. There's no one who can generate randomness for the next block, and so on. So that's the reason why we need to make sure that our randomness always generates some output. It should be guaranteed to output a result. And of course, we need the constant runtime property, because we want each epoch to generate the randomness for the next epoch, and each epoch has a constant amount of time to generate the randomness. Okay. So today I'm going to start talking about a different approach to this random number generation. we're going to keep some of the good parts of the previous approach. So one nice property of this approach using commitment schemes was that even if one player is playing honestly, even if we have one player who's really playing uniformly at random, then the whole result would be a uniform random result. So this was a great property, and we definitely want to keep it. And the way we will keep it is that we will still want each player to choose some input or some number xi, and we will generate our randomness in the same manner as before. So we will always say that our final random result is the sum of numbers that are generated by everyone modulo n. Or if we are generating a binary sequence, we can say that our random number is just a random string, is just the XOR of all the inputs that all the players gave us. So we're going to keep step 1 and step 4. But now we want to replace the middle with something else, and we want to replace it in a way that basically everyone is forced to reveal. We want to make sure that it is impossible for a player to say, I don't reveal. Okay. And now this is a bit counterintuitive, right? Because how can we force someone to do something, especially if you're saying that deposits are not enough and the player might not be rational, they might be fine with losing all their money and so on. But actually it's doable. And I'm going to start talking about this. What we want to use is, well, eventually what we want to use is something called publicly verifiable secret sharing. But I'm going to start with talking about secret sharing itself. And then we will see how we can use secret sharing for generating random numbers. And then the publicly verifiable part is something for the next session, probably. Okay, so what is secret sharing? So here's the scenario I want you to consider. So let's say we have some party that has a secret. So Alice knows the secret. And let's say that this secret is called S. And let's say that this secret S is just a number between 0 to n minus 1. So again, as usual, what I want to do is that I want to do all of my calculations modulo n. So I assume that Alice knows the secret, and this secret number is one of the numbers between 0 and n minus 1. Now, what Alice wants to do is that she wants to share this secret with some of her friends. So let's say that there are also a number of friends. So let's say the friends of Alice are, let's say, friend 1, friend 2 to friend m. And what Alice wants to do is that she wants to send a share of this secret, and I will talk about what I mean by a share. She wants to send a share of this secret to each one of her friends. Okay, so Alice sends a secret share Si, and this is again a number between 0 to n minus 1 to each of her friends, to each friend Fi. And now the property that we want to have is that we want to say, we want to have some number t, and we want to say that if t of the friends come together, they should be able to find the original secret number S. But if fewer than t of the friends come together, they shouldn't be able to find any information about S. So our requirements are that every t friends can somehow combine their shares obtain the original secret S. But if we only have T minus 1 of the friends coming together, they shouldn't be able to understand and to figure out anything about the secret. So every group of T minus 1 friends, T minus 1 friends can find no information about the secret. Okay, so this is what we want to do. We want to make sure that we somehow divide this secret up into several different parts. So each friend Fi is going to get a part or a share Si. And then we want to also have some threshold T, and we want to say that if T of the friends come together, they should be able to figure out what the original secret was. But if fewer than T of the friends come together, they shouldn't be able to find any information. And again, when I say they should not be able to find any information, that means that they shouldn't be able to rule out any values for this secret. So from their point of view, even if they put together all the information that they have, all of their shares, they shouldn't be able to say, even rule out one possibility for S. From their point of view, S should be possibly any of the N different choices here. Okay? So this is what we want to build. And of course, the challenging and interesting part of this is to decide how Alice can create these secret shares and send them. So one thing that we can assume for sure is that we can assume that each secret share is only told to the friend that should know that secret share. And the way we can do that is just using public key cryptography. So if I want to send some share S1, let's say, to my first friend F1, I would just encrypt it using F1's public key and send it to F1. And then I would be sure that only F1 can read that share S1. So in terms of communication, we're just assuming that Alice can send messages basically using this encryption that only a specific friend can open. So the problem is not how to give the shares to the friends. The problem is actually how to define the shares and how to generate these shares. Okay. And what we use here is a very basic idea in the algebra of polynomials, and this is the basic idea. So consider some polynomial of degree n. Let's say I have a polynomial p, which is of this format. It's a0 plus a1x plus a2x squared, so on, to an x to the power of n. Okay, and for now, let's say that this polynomial p is just a polynomial with real coefficients. So let me fix this. Okay, so let's say that p is in Rx. What this means is that basically all of these coefficients, a0, a1, a2 to an, are real numbers. Okay, let's say all of these are real numbers. Now, one very basic result for polynomials is that if I give you n distinct points of this polynomial, then you will be able to uniquely find the polynomial itself. So p of x equals this. Oh, actually, I need n plus 1. So basically what I want to say is that suppose I give you a bunch of points. Let's say I give you some points x0, y0, x1, y1, and so on, and xn, yn. So I give you n plus 1 points, and I tell you that this polynomial goes through all of these points. So if I tell you that p of x0 is y0, and p of x1 is y1, and so on, and p of xn is yn. So if I give you n plus 1 different points, and I say that this polynomial goes through all of these points, then these points basically give us a unique polynomial. And let's see why this is the case. Actually, this is very basic and easy calculations, but let's just do an example. So these things determine a unique P. Okay, so here's an example. Let's say I want let's keep it simple. So let's say I want a quadratic polynomial of this form. P of x is a0 plus a1x plus a2x squared. That goes through some 3 random points. So let's say I want my polynomial to go through, for example, 0, 0, 1, 2, and 2, 4. Okay. So why is this polynomial unique? So what does it mean if I say my polynomial goes through 0, 0? That means that p of 0 should be equal to 0. Right? So if I just write this down, I should have p of 0 equals 0, but p of 0 is this polynomial at 0, so this is a0, then a1 times 0 is 0, a2 times 0 squared is 0, so the value of the polynomial at 0 is just a0, so I know that a0 has to be 0. Now I know that p of 1 should be 2, so I can just write what p of 1 is. P of 1 is a0 plus a1 plus a2. So this is 2. And I also know that p of 2 is 4. So p of 2 is a0 plus 2a1 plus 4a2. And this is 4. Okay. Now I just have to find the values here for a0, a1, and a2. And this can just be done using Gaussian elimination or any other way of solving this system. So a0 we know is already 0, so I can just remove it from here. So I know that a1 plus a2 is 2, and 2a1 plus 4a2 is 4. Okay, so I can just take twice this equation and subtract it from this one. So I will have minus 2a1 minus 2a2 minus 4. And then I can just sum these up. So the a1s go away. I will have 2a2 is 0. So I will have that a2 is 0. And if a2 is 0, then a1 is 2. Right? So as you see, I could just solve this whole system, and I could figure out that a1 has to be 0, a0 has to be 0, a1 has to be 2, and a2 has to be 0. Okay, and so my polynomial is basically just p of x equals 2x. Right, and this is a polynomial that goes through all of these points, and it's also unique because this was the unique solution of this system. Now, what happens in general? In general, when we want to find a polynomial like this, we have all these coefficients that we have to solve for, and there are n+1 coefficients. So if I give you n different points that this polynomial has to go through, these n different points give you n equations, and it's actually easy to show that the equations are linearly independent. So if you have n equations and n unknowns, it has a unique solution, assuming that the equations are independent. So it's pretty easy to see that you can denote any polynomial of degree n by n+1 different points that the polynomial goes through. And of course, here I'm assuming that all of these x values are different, because otherwise it wouldn't work. Okay. So now this basic idea that we used in Rn actually works in pretty much any other field. So instead of R, what I can do is that I can say, okay, I don't want my coefficients to just be real numbers. Maybe I want my coefficients to come from some other field. So I can say that I want, instead of saying that every coefficient is a real number, maybe I want to say that each of a0 to an are just a number between 0 to p-1, where p is like a huge prime number, so some modulus that we're using again. Okay, yeah, sorry if I have to say maybe q because I'm using p for the polynomial, so let's say. Now, if I have something like this, again, I have the same kind of situation where if I'm given n+1 different points, then I have a unique polynomial. Okay. Now, what's interesting about this is that if instead of n+1 different points, I'm just given n different points. So suppose that I just don't have one of these. Then we are in a very different situation. And actually, I cannot know almost anything about my polynomial because I can change my last point to be anything and it will always have a solution. Okay. So here's the thing. Here's the secret sharing scheme. Remember that Alice has m friends. And any t friends should be able to know the secret S. Okay. So basically what I want is that any t of them, if they come together, they should be able to produce this. So what if I just use some polynomial to encode my secret, and then I give each of my friends one point that this polynomial goes through. Okay. And if I choose the degree of this polynomial correctly, if I choose a polynomial of degree t-1, then any t of my friends can find the polynomial based on the points that they have received, but any t-1 of my friends cannot find anything. So this is the basic idea that I'm going to use. Okay. So here's the thing. First of all, we assume that this secret S, well, we actually already assumed this. We said that this S is between 0 to n-1, but let's actually use a prime number there. Let's say this is between 0 to q-1, where q is like a huge prime number. And here also, let's say all of them are like this. Okay. So I have this secret S, which is again between 0 to q-1, and q is a large prime number. Now, here's what Alice is going to do. Here's our protocol. So step one is that she just chooses a random polynomial of degree t minus 1. So Alice chooses a random polynomial of degree t minus 1. So how would this polynomial look like? It would be something like this. P of x is a0 plus a1x plus a2x squared, so on, to at minus 1 x to the power of t minus 1. Okay, now, but how does this work? Well, basically what we want to do is that we want to put our secret in a0. So a0 would be my secret. Okay, but each one of a1 to at minus 1 are chosen randomly. Okay, so basically she creates a polynomial, she puts the secret s into the first coefficient a0, and then she chooses all the other coefficients uniformly at random or using any other source of randomness. Now, so what we want to do is that we want to make sure the others cannot figure out what a0 is unless they have t of the shares. So here's how I define the share. So I would say that to each friend fi, Alice sends this particular share. So the share that she sends to friend number I is just the value of this polynomial at point I. Okay, and let's just assume that all of our calculations are modulo q. So I have this polynomial and I give this value modulo q. Okay, and also here everything generally, we just assume that we're not calculating with real numbers, where all of our calculations are in the field of integers modulo q. Okay, so now what happens? So each one of the friends just knows one valuation, one point that this polynomial goes through. So if t of the friends come together, they have t different points that this polynomial goes through. So they can just write these equations like this example that I had here, and they can find the values of each coefficient ai. And specifically, they can find the value of a0, which is the secret. So if I have t of the friends coming together, they can find the secret. But now what happens if t minus 1 of the friends come together? Well, the problem there is that they will only have t minus 1 of the points that this polynomial goes through. So they can write some equations again, but they will have t minus 1 equations, but they have t unknowns. So the unknowns are these coefficients ai. And since they have t unknowns, they cannot really, they have more unknowns than equations, so they cannot really solve it uniquely. And actually, they cannot find any information about a0. So a0 can be anything. Now, how would we see that? Well, basically, if I want to just belabor this point a bit more, what does each friend know? So I have friend f1, and what they know is the value of this polynomial at point 1. I have friend f2, and what they know is the value at point 2, and so on. And I have ft, who knows the value at point t, right? And so on. And there's, of course, goes to fm, who knows the value at point m. Now, what is it that we want to find? We want to find a0. But a0, or our secret, is basically the value of the polynomial at point 0, right? Because if I set x to 0, then all of these terms would be 0, and I will just get a0. So basically, the problem that we have is that these friends can know the value of the polynomial at several different points. And based on that, they want to be able to calculate the value of our polynomial at point 0. Now, as we saw, if t of these people come together, they can uniquely calculate the value at 0, and they can find the secret. But if t minus 1 of them come together, then they only have t minus 1 points of our polynomial. And then we can have any value at point 0, because again, here, what I said was not just that, here what I said was not just that these things determine a unique polynomial, but also that such a polynomial exists for any set of numbers like this, for any n plus 1 pairs of numbers. So in other words, if I have t minus 1 or fewer of the friends coming together, they find no information about a0. Okay? And this is like the perfect kind of secret sharing, because now I have all the properties that I wanted. Any t friends can find the secret, any t minus 1 friends can find nothing. Okay? So let me answer the question. One question here is that if Si is P of I modulo Q, why doesn't the polynomial generated from the M pairs differ from P of X? Oh, okay, so I'm doing all of my calculations modulo Q. So even here, I'm defining, let's say I'm defining P of X as this thing modulo Q. Okay. So basically what I'm saying is that here what we had were polynomials that were real, so our coefficients were real, and the values that X could take were also real values. But we don't need this. We don't need this assumption. As long as we have a field, we can do all of these calculations that we had here. Basically, we can do Gaussian elimination. So instead of saying that the AIs and the X are real numbers, I can say that all of my AIs and even my X are just natural numbers between 0 and Q minus 1, as long as Q is a prime number. And then all of these things go through. So you can just do the same Gaussian elimination also. Okay. So now we have this secret sharing scheme, and we are kind of happy with it. But now the question is, how can I use this to actually generate randomness? So let's go back to our random number generation problem. Okay. Now, what was our random number generation? So let's go back to this figure here. So in each epoch, we had R minors, and we want these R minors to come together and generate randomness for the next epoch. Okay, so let's say the players that I have are minor 1, minor 2 to minor R. And remember that I said I want to keep all the good parts of the random number generation using commitment schemes. So I wanted to have this initial phase. So I wanted to have step 1, in which each minor just chose some random number. So each minor mi chooses some random number xi. And again, here we're going to assume that this is between 0 to q minus 1. And then we also had a final step that I want to keep. So this was our final step. In the final step, we would just say that the final random output is just the sum of all the numbers that the minors have chosen. Right? And of course, it's modulo q. Okay, so we want to keep these two. And the reason we want to keep these two is that we want to keep the property that even if one of our players, even if one of our miners is honest and actually generates this xi uniformly at random, then our final output would be distributed uniformly at random. So we're going to keep this. What we're going to change is the middle. Now, previously, what we had was that they just do a commitment scheme, right? But the problem was that a miner might choose not to reveal. So now we do something more than a commitment scheme. So in step 2, here's the thing. I want each one of my miners to actually create, to actually use this value xi as their secret and share this secret with the other miners. Okay, so think of each of our miners as Alice. She knew a secret and she wanted to share it with her friends. So now I'm just saying that every miner knows a secret, which is this number xi that they have chosen, and they want to share it with their friends. But of course, I also need some threshold t. So let's say that I also have a threshold t. So I have the players. I also have some threshold t, which is, let's say, less than r minus 1. And let's say it's also more than 1. Okay. So in the first step, each miner just chooses some value xi. In the second step, I would say that the miner mi treats xi as their secret. And gives shares of this secret. So gives shares, let's call them xij of the secret to every other miner, to every miner mj who is not the same as mi. Okay, so the only difference with the previous scenario is that previously we had just one person who wanted to share a secret. We just had Alice, and she wanted to share her secret with her friends. Now we have a lot of miners, and each miner wants to share secrets with all of the other miners. Okay, so the miner does this. Now we're going to use the commitment scheme anyway. In the next step, I would say that this miner mi chooses some nonce. Let's call it ni, and computes or publishes the hash. So this is hash I, which is the hash of his chosen value xi and this nonce ni. So we have the same commitment as before. Now again, this part is the part where we wait for everyone to commit. But now our commitment is not just the hash, it's also these shares. So when I say we wait for everyone to commit, that means that we wait for them to publish the hashes, hi, and we also wait for them to publish the secret shares, xijs. Okay? Now, so if you think about it, what's happening after this point? So I've had 3 steps already, and the difference is that previously I used to just share my hash, so no one could know anything about my actual value xi. But now I'm not only publishing my hash, I'm also publishing these secret shares xij of my secret xi. Now what this means is that every T of the other miners can just come together and put these things together and say, okay, here's the value of Xij. So I don't have as much secrecy as I used to have in the commitment scheme. When I was using a commitment scheme, no one could find anything about my value Xi based on just the hash. But now actually, it's a bit less secure from the point of view of every single miner, because we know that any T miners can come together and basically open the hash. But what we're doing here is that we are assuming that the number of dishonest miners is less than T. Okay, so let me add this assumption here. Our assumption is that there are less than T or fewer than T dishonest miners. And actually, if this is the assumption that we're making, then we should probably also assume that, well, we should also assume that R is at most 2T, for example. Okay, so if I know that there are fewer than T dishonest miners, I can be sure that after sharing these values, this secret sharing here, after sharing the Xij and sharing my hash, no one else knows my value, right? Because the only way that someone can figure out my value is if T miners come together, and we are assuming that the number of dishonest miners is less than T, so T miners will not come together. Okay, so at this point, I have given all of my shares and everything, and everyone else has also done the same thing. We are all committed to our shares. So the next step is that we just open all the commitments. So in step 4, here's what happens. Each miner MI publishes several things. So what are the things that we have to publish as a miner? Well, first of all, we want to open our own hash, right? So I would publish Xi, and I would also publish the nonce Ni. So this is used by others to be able to verify that I've announced and committed to the right hash. But additionally, I would also publish all the shares that are given to me. So I would publish Xji for every j that is not equal to I. Okay, so any share that any other miner has given me would be published now. Now, how were these shares given to me? Well, these were also given on the network, so everyone else was also seeing all the messages that were going between us. So everyone else has seen that this particular miner has given me a particular share, but it was encrypted using my public key. So when I'm publishing this, I'm basically decrypting it and publishing the decrypted version. And again, everyone can verify that this decryption was done correctly. Okay. And then step 5 is just as before. So we just say that our random number R is the sum of all the numbers that were chosen by the miners. And of course, we take it modulo our big prime number Q. So yeah, this is basically the only difference that we made here, was that we said instead of just committing to a hash, you also send out shares of your secret. And then here, when you want to reveal, instead of just revealing your hash, you will, instead of just revealing your choice and nonce, which basically verifies your hash, you also reveal all the shares that you have received from the other miners. Now, why does this work? So first of all, we have the commitment scheme as before. So because of the commitment scheme, I can be sure that no one can change their choices after step 3. right? So they have already committed as soon as they publish their hash. But the problem that we had previously was that in step 4, we might have a malicious miner or an attacker who decides not to reveal. But what would happen in this case? If they decide not to reveal, then we can just build the value xi using the shares that were given to the other miners. Because we just need the shares of t different miners in order to make xi. And we assume that the number of miners is at least 2t, and the number of dishonest miners is less than t, so at least t shares are given here. So everyone on the network can use those shares to find the original value of xi, even if the miner himself does not publish that original value. Okay? But this seems all good and working, but there are still a few problems here. So one problem we will have is what happens if the miner just sends invalid shares, right? So it's possible that I send shares to the other miners that make no sense and they cannot be combined to create a valid polynomial. Well, what we would do here is that we again can use deposits. We can say that if after all the shares are revealed, it's found out that some miner was cheating and they sent conflicting shares to the other miners, we will just ignore the value that was sent by that miner, and we will also penalize them. We will burn their deposits or confiscate their deposits. Now, why is this any better than just confiscating deposits when we had, let's say, a commitment scheme? Because in this case, the deposit will be confiscated even if the miner reveals. So the miner has to decide here whether they want to cheat or not. So when they're sending these shares to the other miners, they have to decide if they want to really create the shares using this protocol and give valid shares to the other miners, or whether they want to cheat and give invalid shares. But at this point, the miner does not know anything about what the other miners are going to choose, about the random number that the other miners are going to choose. So if at this point the miner decides to cheat, and if we can detect it later on, that's fine, because we can always just exclude the cheaters, and they cheated without knowing the result, so they cannot really tamper with the random number that we're generating in the end. You see, so the timing is really the key here. So I just add this here. Let's say penalize any miner MI who published invalid shares. And ignore the value that they sent, ignore the xi that they sent. Okay, so once again, here the miner is choosing whether they want to cheat or not before they know the value of the other miners, and they will be found out and penalized for it anyway, so the cheat doesn't really work. Whereas previously, when we were talking about this commitment scheme, the miner could choose to cheat when they were revealing their value. So at this point, they could already know the values chosen by the other miners. So it made sense for them to cheat, and they could actually change the distribution of the final value. So again, the timing is the most important aspect here. Now, using this simple idea, we can actually generate a random number. And again, the guarantee that we have is the same guarantee that we had before. Even if we have one player who is honest and truly playing uniformly at random, so even if we have one xi that is chosen uniformly at random between 0 and q minus 1, then the final result, since it's just a sum or XOR of all of them, would also be uniformly at random, distributed uniformly at random. So this is great, but now we have One final problem, actually, and this is something that I will talk about in the next session. And the final problem that we have is that we have too much communication now. And all of this communication is going to happen on the network. So when we were talking about our network model, we said that the way you send messages to others is that you use a gossip protocol, right? So you create a message, you give it to the nearest node on the network, and that node validates this message just like a Bitcoin network and gives it to all of their neighbors, and they give it to all of their neighbors, and so on. So sending messages is actually an expensive operation in a sense, because everyone on the network has to propagate them. Now, when we were using commitment schemes, let's just count how many messages we had to send. So here, every miner had to just send one hash, right? Well, okay, hash and signature, but that's one message. And then they had to send another message here, which basically reveals it. So we had 2 messages per miner. So if I had R miners, I would just send 2 times R messages. But now, see what happens here. Here, each miner should not only announce their hash, but they should also give these secret shares to the others. So each miner now is sending R+1 messages here, right? Because, sorry, sending R messages here because they're sending R-1 shares to the other miners, and they're also sending a hash. And similarly here, they have to send R messages. So in a sense, the communication complexity is now higher. So thinking about it here, in terms of the number of messages that have to be propagated on the network, I need to propagate order R² messages, right? Whereas previously, when I was talking about commitment schemes, I only had to propagate order R messages. So now this is a bit harder on the network. We can still use this. So this is already good enough for having a proof of stake. But then if we use this, we have to make sure that, that our epochs are long enough for all of these messages to be delivered. So in practice, you have to think about this. You have to think that I have R² messages that have to go through the whole network. How much time would that take? And then you have to set your epoch to match that time. So basically, it takes more time for us now to generate the random number, but we have a better security. So in the next session, I'm going to talk about ways of maybe reducing this communication complexity back to order R. Okay, so that's all for this session. I'll stay if you have any questions, but this is the end of the session and you can leave. So have a great day.